Hi everyone, my name is Boris, and today I'm going to be talking about MATS, an interpretable trajectory forecasting representation for planning and control. Prediction is a core component of modern robotic systems, especially those that interact with humans such as autonomous vehicles. A notable use case is informing downstream motion planning and control modules, making them more proactive and interaction aware. Currently, most trajectory forecasting methods produce future tracklets or distributions thereof for each agent in a scene. This is an intuitive output representation that matches common evaluation metrics. However, a majority of planning and control algorithms reason about system dynamics rather than future agent tracklets. As a result, in this work we investigate more efficient output representations for planning and control. So naturally, the question now is, can we meet in the middle? Can we produce a dynamical system as our trajectory forecasting output? And we argue that the answer is yes. We propose mixtures of affine time-varying systems, MATs, as a trajectory forecasting representation that maintains interpretability, improves planning efficiency, and maintains the ability to produce multimodal predictions. Below, we can see the formula for a mixture of an affine time-varying system, or specifically one component thereof, and in particular, our model produces the coefficient matrices A, B, and Q, and we'll talk a little bit more later about what some of these mean and how they can be interpreted. So we first evaluated our approach with an illustrative charged particle experiment visualized on the left. One of the particles, in gray, is the ego robot, which follows a predetermined trajectory. The other, in green, starts with some initial velocity but is then acted upon repulsively by a force proportional to the particle's inverse square distance, which is a nonlinear interaction effect. On the right, we can see the A matrix that our model produces. The A matrix is responsible for modeling the autonomous evolution of the system. And we can see that the bottom left submatrix lights up during the interaction, and this corresponds to the robot's increased effect on the agent. This validates MATS's ability to model nonlinear interactions in an interpretable fashion. And the reason why the bottom left submatrix is the one that we're focusing on is because these subblocks are corresponding to the state being the states of the agent, like the overall system state being the states of the individual agents concatenated one after the other. And we take that the agent 1 is the ego robot, and agent 2, which would be represented by the second row, is the other agent. We also evaluated our method on the new scenes dataset, and here we can see some qualitative plots of the model's predictions. We can see that it produces sensible forecasts even in quite dense and cluttered environments for both vehicles and pedestrians and really any other class of agents. So we can also apply the same interpretability analysis with the new scenes dataset. And in particular on the left, we can see a scenario where the ego vehicle in red is crossing an intersection. On the right, we can see visualization of the B matrix over time, which is responsible for modeling the effect of the ego vehicle's control on other agents. We can see that specific entries in the B matrix light up, or that is, increase in Frobenius norm magnitude, as the ego robot enters the intersection. Interestingly, these 5 standout rows that are actually having interaction over, have magnitudes that change over time, correspond to other vehicles in the scene, indicating that the model predicts that the robot has the most effect on other vehicles when it is in the middle of the intersection. This is also visualized by the thickness of the lines in the left figure. Now, we've also evaluated how our method can be coupled with a downstream planning and control algorithm. And in particular, we've developed a novel planning formulation that can take into account the multiple predictions that our model makes to produce multiple trajectory plans for the future. And in particular, these multiple trajectory plans are anchored in that the first few time steps are constrained to be the same, and then later on, as visualized here by the different colors, later in the plan, they can diverge. Now, most importantly, where you really see the benefit of using the MATS representation is, and this is one very notable case, is in the computational planning efficiency. So when we compared to a recent GPU parallelized tracklet-based planning approach, it was able to plan within a quarter of a second one trajectory considering one other agent. And this was a work from ACRE 2018. In that same amount of time, our CPU-based and MATS-based planner was able to plan 3 simultaneous trajectories, considering 24 other agents and their associated 552 directed interactions. So, in summary, choosing a planning-aware output representation for trajectory forecasting yields significant benefits downstream and better facilitates the integration of trajectory forecasting with modern robotic systems.